Hi, I'm Arun Thomas, and I love systems, operating systems in particular. And so my talk is titled, You're Not Expected to Understand This, But You Will. And so it's about context switching on Unix v6 and FreeBSD. So context switching is the mechanism that allows for sort of time sharing and multitasking. And so time sharing multitasking is essentially how a computer is allowed to be shared by multiple concurrent users and multiple concurrent applications. And it's a neat trick, and Unix's great time sharing support was a big reason why it took off. It was a big leap forward in usability. And so we'll talk a little bit more about how this all works on Unix, particularly Unix v6, and we'll also see how it works on our FreeBSD. So some things have changed over the years, but the overall scheme has fundamentally remained the same. So my title is referencing a famous comment, you are not expected to understand this, in the switch function and the Unix v6 code. And so it's pictured here. And this is the code that accomplishes the context switch between processes. And those who've read the Unix v6 source code sort of like the comment, and you started seeing people wearing sweatshirts, t-shirts, and baby onesies with you are not expected to understand this on there. And yes, I am wearing the t-shirt pictured on the slide. I thought the button might be a bit much, so I didn't put the button on. But yeah, it sort of took off in the kind of hacker community. So the history is kind of interesting. So Dennis Ritchie actually had sort of a comment about the comment. And so many people who read the comment thought it came off as sort of cocky, or as Dennis Ritchie put it here, as sort of an impudent challenge. The Unix authors sort of meant it more in the vein of, yeah, this won't be on the exam, so don't feel obligated to dig into all the details of this crazy context switching code, but people took it the other way. Another amusing bit that Ritchie shared is that it turns out the code was actually like buggy, and that the Unix authors didn't completely understand it either. So that was actually kind of funny. That was another thing that Ritchie shared. And so the code was actually rewritten when they moved to Unix v7 and the second architecture that Unix supported, and the comment disappeared. So the moral of the story is that context switching can be tricky even for the creators of Unix. You have to get really deep into the CPU details and make sure it's right, because if you don't, horrible things will happen. Your system will completely crash. So I'll give you sort of an overview of my talk. So the goal is basically we'll learn about context switching, since it's the fundamental mechanism that allows for users and applications to share the system safely. So we'll start off with a little bit of history of Unix and Unix v6 in particular. Then we'll talk a bit about the core abstraction in Unix, the process. It's the key abstraction that allows for sharing of system resources. Then we'll talk a bit about context switching on Unix v6 and look at the switch code again, sort of a compressed version of it. We won't go into all the details. Finally, we'll look at context switching on a modern Unix, FreeBSD. And although it's been 40 plus years since Unix v6, the process abstraction and the mechanics of context switching are fundamentally the same. And there have been changes, of course, due to advances in OS features and hardware, but the important bits are the same. So let's talk about Unix. A lot of people have been talking about Unix, and I'll talk more about Unix in this talk. So Unix, or the Unix time sharing system, was created by Ken Thompson and Dennis Ritchie, and it influenced basically every operating system that followed it. So Thompson and Ritchie started working on Unix in 1969 at Bell Labs, and you can see them both here in front of a PDP-11. So Ken and Dennis both worked on Multics beforehand, and this was like an earlier time-sharing system and a really influential system as well. And they drew several ideas from Multics that made their way into Unix, but they wanted to build a much simpler time-sharing system that allowed multiple users to share fairly inexpensive hardware, so the DEC PDP line, the DEC PDP machines. So Multics was designed for mainframes, which are more expensive, much more expensive. And so Unix was a big leap forward for users. A lot of people really liked using Unix because it gave a really kind of nice, interactive, responsive environment, especially for programmers. So it allowed multiple users to log into a terminal and share time on the PDP-11, which is fairly inexpensive. And the shell made the system very productive. And so this was a big deal in the pre-PC era. So nowadays, you kind of take it for granted. You have, I don't know how many machines yourself. Back then, you had the one big machine, and lots of people logged into it if they were lucky. So this was kind of a big deal at the time. So Unix v6, the version of Unix that we'll discuss in this talk, was released in 1975. It was roughly 9,000 lines of code, so it was small enough that it could be studied in a university course. And indeed, people did teach Unix and OS courses. In particular, John Lyons, professor at the University of New South Wales in Australia, prepared a really detailed line-by-line commentary of the Unix v6 code for his OS course about like a year after the Unix v6 release. And it was really exciting for students to be able to study a real system in their OS course. So eventually, AT&T realized they could make money off of Unix, and so they changed the licensing terms to allow only official Unix licensees to study the code. This didn't seem to stop people from studying the code. People would create unauthorized copies of the Lyons commentary for their study. So people were making photocopies of photocopies, and you can sort of see some unauthorized copying happen in this picture. So I gave an early version of this talk at Papers We Love Boston, and so one of the attendees showed up with his unauthorized copy of Lyons, and it was kind of cool that he still had it and like really kind of treasured it. So yeah, Lyons was a pretty big deal. I mean, it's part of the reason why the You Weren't Expected to Understand This got so big. A lot of people read the code and the commentary, and it kind of took off from there. So the fundamental abstraction in Unix is the process, and so it's a program that's being executed. And so the process address space has some code, some data, some heap, and some stack. And the process model was adopted from Multics, but the Unix simplified it by dropping shared library support. And so the process is a form of virtualization. And so one of the Multics papers described processes as virtual processors. And so you can see that here in this diagram. It's from one of the Multics papers. You have a virtual processor and along with a memory address space associated with it. And so that basically defines a process. So there's some, to support the process abstraction, the hardware implements a few key hardware mechanisms. So the CPU has like your standard general purpose registers, program counters, stack pointers, but more importantly for the OS perspective, the CPU also has a mode register, and that specifies whether the CPU is running in user mode or supervisor mode, aka kernel mode. So code running in supervisor mode can perform privileged operations like setting up the page table and disabling interrupts. And you don't want regular application code able to access these operations or bad things will happen. That'll basically destroy your system's reliability and security, and so yeah, definitely not good. So the CPU also has support for traps, so interrupts and exceptions, and has various control and status registers related to trap handling. For instance, where does the CPU find the trap? Or where's the trap vector table? How do you disable interrupts? That sort of thing. One of the most important traps is the system call trap. Since applications can't perform privileged supervisor actions, the kernel has to perform these services on behalf of the application. So that's a fairly important trap. There's also a timer trap that allows the kernel to kick off an application that's hogging the CPU, and this is important for implementing preemptive multitasking. The CPU also has a memory management unit and associated control and status registers. So the MMU is used to implement virtual memory and protection. So each process has its own address space, and each application can't stop on each other's memory. So there are two kind of main models for this, and so there's like segmentation and paging. So modern CPUs use paging, but the PDP-11, which Unix v6 supported, use segmentation. And so the picture represented here represents sort of a superset of the CPU context that needs to be saved and restored on a context switch when you switch between processes. So when an operating system is running, the OS is doing multitasking, and it's sort of fundamental to building for time sharing and building a responsive system. And so this is what multitasking looks like in action. You have a bunch of processes, and the OS is constantly context switching to the next process. You can picture the OS as sort of the bouncer at club CPU. If you get too rowdy, you get kicked out. And if a VIP buys out the place, you get kicked out as well. But you can probably come back the next day. So this is sort of constantly happening. Processes are getting swapped out, or context switched out, and context switched back in. So context switching can happen when the process's time slices up. So in a multitasking system, each process is given a share of CPU time, and the process will get kicked off when the timer interrupt fires, and that's how the kernel takes control and is able to enforce the time slice. And so processes also get kicked off for other things like interrupts and exceptions, such as disk interrupts, system calls, and page faults. And so this is sort of like the steady state for what's happening in an operating system. Processes keep getting juggled. So if you look a little bit closer at what happens on a context switch, so context switching, as I mentioned, is how the system transfers to running the next process. So in this case, process 2. And so context switch requires a transfer into and out of kernel code. So the two processes are running user mode, and so the kernel needs to gain control to kind of manage the context switch. And so this is done by the CPU will kind of transfer control into kernel mode and run the kernel. So if you look at this picture a little more carefully and look at kind of the orange bit, which is the actual context switch, specifically, so a timer interrupt is triggered because the process's time slices up. The CPU will switch into kernel mode, and then the CPU and kernel together will save process 1's context somewhere in one of the kernel data structures. Then there's a scheduling decision, and then the CPU and the OS together will work to restore that context and then jump into the next process. So that process 2 can begin running. And the context saving and restoring is CPU specific, but the scheduling step is common across architectures the OS supports. And so the overall flow for context switching is essentially you save some context, you make a scheduling decision, and then you restore the context. So with that sort of background, we can look at the Unix v6 switch code again. And so this is a very simplified version of what I showed earlier. You can kind of see the flow of saving context, scheduling, and restoring the context. So the switch routine, you start off, and this is saving the context. You may not be able to say that in the back, but there's a save U function that saves some of the PDP-11 context in the U area, specifically the UR-save field. So the U area, or the user struct, is a kernel data structure that holds the CPU context. I should also note that things are a little bit more complicated because some of the context has already been saved before the switch function is actually called. So the switch code will then do some scheduling to pick the next process. It actually picks the highest runnable process. I don't actually show the code, but I'll talk a little bit more about this in a later slide. So after scheduling, once the OS knows which process to switch to, it'll restore the context. So there's a retu function that will restore some of the context, and the sureg function will set up segmentation registers for the next process to set up the virtual address space. And so this is kind of a high level of what happens. You do some context saving, you schedule, and you restore context. And the full details are in Lions, and it's actually fairly complicated, but it's kind of an interesting read. Since I love looking through old processor manuals, these are some screenshots from the PDP-11 manual. So this is specifically the PDP-1140 manual, and so this is a machine described in the Lions commentary. And it's the machine, and so it sort of describes the context, the CPU context that needs to be saved and restored. And so this is actually a superset of the context that needs to be saved and restored. So if you look at it, the PDP-11 was a 16-bit machine. So you have 6 general purpose registers. You have a stack pointer for kernel and user, and then you have a mode. You have current and previous modes, and so you can have either user or kernel mode. And you also have some segmentation registers, and this is how you set up the virtual address space. And you also have a trap table for system calls and various things like that. So this is kind of the state that you'll need to kind of save in the context switch code. So Unix v6 had a really simple scheduling policy. It was really easy to understand. So the switch code basically would just loop over an array of proc structures to find the highest priority runnable process. And so it would look at the, you may not be able to say this in the back, but it'll look at the status field, the flag field, and the priority fields to make that determination. Essentially, they want to find a process, the highest priority process that's actually runnable. And so there's a lot more, this is much simpler than modern day scheduling algorithms where you have a bunch of queues and all of these things. It was sort of the nice thing about Unix v6. It was a very simple system and easy to kind of understand, but yeah. So if you look at sort of modern Unix, and FreeBSD in particular, which is a modern day Unix, the process abstraction is fundamentally the same, but there's been some changes along the way. And so some of the changes, back then you didn't have threads, you didn't have dynamic linking, you didn't have mmap, you didn't have scalable memory allocators. So things are a bit more complicated, but fundamentally they kind of like standard, the process abstraction is fundamentally the same with some new additions. There have also been a number of advances in scheduling algorithms and data structures. No longer do we have this single array of proc structures. Instead, we have proc structures organized in multiple queues, and even the proc structure itself in FreeBSD is a lot more complex, and I'll show this in the next slide. FreeBSD is a kind of a sophisticated scheduling algorithm called the ULE scheduler, and it's a lot more sophisticated than the kind of simple Unix v6 scheduler. And so the hardware landscape has changed since the PDP-11. So some of the kind of architectures that you see nowadays are x86, ARM, and RISC-V. So ARM v8 and RISC-V are fairly newish architectures. And there have been improvements in MMU since the PDP-11. So paging is sort of common now. And then there's been different page table structures. You've got TLBs and address space identifiers. You have multi-core now, NUMA, heterogeneous cores, symmetric multi-threading. So this complicates scheduling algorithms. So does power management. So the hardware landscape is definitely a lot more complicated. And as a result, the OS is a lot more complicated. But the core mechanisms described earlier, so having modes and MMU and traps, are still found in modern architectures to support the process abstraction. So this is a picture of the proc structure in Unix v6 and FreeBSD. And so even the people in the front won't be able to read the FreeBSD proc structure. It's definitely a bit more complex. And the thread structure is even larger, and so it's also fairly complex. And so, I mean, the reason why, and Ryan mentioned this as well, is that like there's been 40 plus years of development, and so FreeBSD just has a lot more functionality, and as a result, like a lot of the data structure is a lot more complicated, the algorithms are more complicated because there are features and things that need to be implemented. So this is sort of interesting because not only the proc structure is more complicated, but you have the queue things, the scheduling algorithms, and so you kind of see the evolution of Unix from like a simple system to a more kind of production system, and hardware changes have also caused some of that as well. So the OS and data structures are more complicated. The hardware landscape is also more complicated. So this is what x86 64 looks like, or AMD 64 if you prefer. So it's a little bit more complicated than the PDP-11. So you have general purpose registers and segment registers. You have control registers for MMU settings. You have GDTs and LDTs. You have an interrupt table. It's complicated. So I won't really go into the details here, but mostly because we missed the reception. Yeah, it's all pretty complicated. And so the context switching code as a result is also complicated. ARM and RISC-V is a little bit simpler because it doesn't have all the kind of x86 legacy, but context switching is sort of inherently complex because you have to get into the details of the CPU architecture. So here's the FreeBSD CPU switch code. It's a very small, compressed version of it. It's actually several hundred lines of assembly. So the kind of basics of context switching, you save the context, you do the scheduling, and you restore the context. That's kind of basic flow. So in FreeBSD, this function is called CPU switch. And so this is and it's CPU specific. That's why it's called CPU switch. And in this case, it's x86 64 specific. So essentially, you'll save the context, and I won't go into all the details, but you'll have to save some general purpose registers to the current process's thread structure. That's where the context gets saved. Then the function will restore some context from the next process's thread struct. So from process 2 from the previous diagram. And so this context includes page table registers, LDTs, segment registers, and the GDT, TSS, and it'll restore the general purpose registers that you saved earlier. So the full details are in the CPU switch code. It's fairly complicated, but you kind of have this basic flow. And you may have noticed that there's no actual scheduling step. And so it turns out the scheduling code has actually moved to a new function called schedSwitch in FreeBSD. And so this is a machine-independent function that is common to all the architectures, basically to reduce code duplication. They didn't want to have to duplicate the scheduling code across all of the different architectures they supported, so they refactored it into a machine-independent file. So this is a very high level of how CPU switching works, and this is sort of critical to multitasking and time sharing. So I've only scratched the surface. For a more complete understanding, you can check out the MIT OS course from 2005. So they studied Unix v6 on the PDP-11, and they used the Lions commentary, and the lecture notes are up. So this is sort of a choose-your-own OS adventure. if you want to learn about x86, you can look at the recent MIT OS course from 2016. So MIT created this Unix clone for x86 called XV6, and so they also created a line-by-line commentary for their clone called XV6. And so that's actually pretty cool. One of my interns is actually taking this class now, and he highly recommends it. If you're interested in FreeBSD and ARM, there's the University of Cambridge L41 course, taught by some colleagues of mine, and you get to dig into the internals of a real production operating system using dtrace, and you also want to check out the FreeBSD design and implementation book. So this is actually pretty cool. So someone created this Unix history repository, and so it's a GitHub repository, and you can track the kind of earliest versions of Unix all the way through modern FreeBSD, and it was really helpful in kind of preparing this talk. It's pretty cool. So in summary, Unix v6 did time sharing well, and it's part of the reason why it took off. It was a big leap forward in usability. Time sharing is not easy to get going. The hardware is complicated. And I hope I kind of gave you a flavor of the complications, especially on x86. So it was interesting looking at the FreeBSD code. So modern operating systems fundamentally do time sharing the same way by using the process abstraction and context switching. And so I hope I gave you sort of a flavor for that. And even if I failed at the task and I didn't get across the importance of the process abstraction and context switching, you'll at least understand my t-shirt now. So thank you.